Okay, today we continue our discussion of conjugate directions method and later on conjugate gradient methods, which are important class of algorithms for solving unconstrained so called non-linear optimization problems. But I begin with trying to give you a solution for this problem, where I said that okay, if you have a function f x given like this, where it is a quadratic function with Q being a positive definite matrix. Then we said that if you apply Newton's method to solve this problem, then you can solve this problem in just 2 steps. So, we shall use this idea of the Newton method to see that we can actually solve this problem in 2 steps. This was one of the homeworks which I had given in just in the last lecture. So, let me just try to solve it for you, but it does not mean that all the homeworks would be solved, because you need to try yourself and be confident about whatever answer you are giving. So, if you look at this, if this is a convex function, so its critical point is the global minimum, and in this particular case this is a strongly convex function and hence has a unique minimum. Now, if x bar is really the minimum, then it must be satisfying grad f x bar is equal to 0, and that would imply in this particular case, because the gradient at x bar is this, or the solution is now. Let me start with a guess solution x naught. X naught is a guess solution, right, starting solution for the Newton's method. Now, once you have taken the guess solution, your next solution, assume that this does not give me the solution, then the next solution is, so this first step is choosing x naught, the next step is getting x1, which is x naught minus the Hessian at x naught is q, so inverse of q into the gradient at x naught. So, that will lead to x1 is equal to x naught minus q inverse q x naught minus q inverse c. So, this q inverse q is identity, so this will cancel. So, this will become x naught, and so x naught minus x naught. So, it is x1 is equal to minus q inverse c, and that is exactly what the solution should be, and hence in just 2 steps you have actually solved the quadratic problem. Now, this sort of problem would continue to be very useful as a demonstration tool. This is usually used as a very important demonstration function to demonstrate things, or prototype function. So, a large number of properties are first checked on this class of functions to see whether algorithms are working well with this class of functions. If they start working well with this class of functions, then they are working well with many other class of functions, they could possibly be doing well with some other class of functions. So, let us go into the conjugate gradient method or conjugate directions method again, and we again follow this book by Anto Neo and Wu Sheng Lu practical optimization, whose reference I had given to you in the last class. Now, our problem would be to minimize this function f x over whole x in R n, where I will follow their notations. So, H is actually the Hessian matrix of f. So, we just write H. Now, of course, A is nothing but f 0, and B is nothing but the gradient of f at 0, because for any x, f of x is the gradient of f at x is nothing but h x plus b. So, you put x equal to 0, so grad f 0 is b. So, in general, we for shorthand we will write g is equal to grad f x, which is same as h x plus b. Okay. Now, if d 0 d 1 d n minus 1 or n distinct, of course, we are only concerned about the case where h, this function, this mapping, this Hessian matrix is positive definite. This is a very important thing, we are only bothered about positive definite. So, if n are distinct conjugate directions, then n distinct conjugate directions, then the linear span of, there is a subspace generated by, is R n, because you see there are n linearly independent vectors in R n and their span would naturally generate R n, right. You cannot have n linearly independent vectors in R n and whose span is not generating R n, because so they will form a basis, since that is what we proved for the specific case when H is positive definite. So, any x star that you take may be the solution. So, any solution of this problem. So, if x star is a solution which is a unique solution, x star is a unique solution and solution will exist for this problem. I have not told you a detail as to why a solution would exist for this problem, but just accept for the time being that the solution exists for this problem, because taking details would push me into much more deeper details. So, we have not done all these things. So, of course, you can always find a minimum, because if you take the derivative and put equal to 0, you will have x star equal to this, and because it is a convex function, and of course, there is a unique critical point, and that will be the global minimum, because the function is convex. So, let x star is a unique minimum of f, say, assume that, then h of x star is equal to minus b, because grad g x star is 0. So, grad of f x star is 0. So, but whatever, x star is an element of R n, and we can write always x star is summation where alpha I are some scalars, some real numbers. Now, let us do one thing, look at inner product for any k among this d1 d2 dk. So, we will ask our questions, what is this? Now, h of x star by rules of simple rules of matrices or linear operators, if you want to say, is nothing but h of that. I hope everyone would agree. You could put I equal to 1 to n also, does not matter. I am just following the methodology of this book. So, I am just trying to maintain their symbol, so that they are if you read this book, you will not get into much trouble. Now, once you do this, then I would have dk h x star would be summation alpha I dk h di. Now, because they are conjugate directions except the dk, everything else would be 0. Dk, when k is not equal to I, this is 0. So, what I finally get is alpha k dk h dk, that is what you will get. So, you see what I am doing is I am trying to compute the alpha i's or alpha k's, whatever, which is nothing but the coordinates of the vector x star, the solution, in terms of the basis d naught d1 dn minus 1. So, now alpha k can be written as dk h x star. Now, because this is positive definite and dk's are not equal to 0, because they are part of a set of linearly independent vectors. So, this is strictly bigger than 0. So, I can write this as dk h dk, basically I can divide it both sides. Now, you also know that h x star is equal to minus b, because I have assumed that x star is the unique minimum. So, what I would have here is alpha k is equal to, see, once I know alpha k, I basically know the x, because that is it. For each k equal to 0 to n minus 1, if I know alpha k, I basically know the x. So, x star can now be easily computed. Once you know from the problem data, you can easily compute, because you have to compute this case for the n alpha k's you have to compute. So, basically in n steps, essentially you really know the solution, right. So, then x star can be now written as summation, there will be a minus sign, I equal to 0 to n minus 1 dk inner product b divided by the same dk h, or I should write k equal to 0 to n minus 1 to be more precise, d h dk into dk. This is exactly the expression of the. So, what have you done? What have I achieved here? I have been able to find the minimum of that problem. Minimum is obtained without inverting h. So, if h is very large, then we really do not want to invert it, because the cost of inverting a matrix is pretty high. and you see this problem data, once B is known, H is known, these two data are known, C is not really nothing to be bothered about this A. B is known, H is known, and D's are known. So, I can easily compute out the X star, and the interesting thing that we have not inverted the matrix H. This is one way of doing it, and another way of doing it is that how to use a more iterative approach. Here what I have done, that I know that X star is a solution. So, I know what is the optimality condition it satisfies for that unique solution, and then I have used the fact that DIs are linearly independent and went in and solved it. The question would be that can I develop some sort of iterative scheme, any sort of iterative scheme, and that iterative scheme would lead to the solution in n steps. Of course, here you see we have solved it in n steps, because for each of alpha 0, alpha 1 dot 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 alpha n minus 1, I have to compute the alpha naughts, right. So, basically I have to change my decays for every alphas. So, for every alpha 0, I have to take d0 and so and so. If my conjugate directions are known, what we can also do is that we can generate an iteration. See, here what we have done is a direct approach. We know that this X star would be, there is a unique minima X star, and that can be expressed as a linear combination of summation alpha I di, and we know that I should be able to, using the fact that these are conjugate directions, I should be able to calculate all these coordinates alpha i's. Once I know that, I can easily write down X star. So, that is essentially the process that we have used, but this is not an iterative process, that is it is more computationally extensive, that is you are doing in n different steps. So, what we can write down is that using this conjugate directions, which are actually not descent directions, we can still write down an iterative line search process where you search along these conjugate directions. So, you have x naught, from there you use d naught to go to x1, x1 is x naught plus alpha naught d naught. So, you at every step basically find that alpha naught. So, what we are going to now interpret and show is that these scaling factors, that is if you are in k and you want to go to k plus 1 for this particular problem that we have studied with xk, we want to show that this alpha k is actually the coordinate associated with xk. This alpha k, this length, right, this alpha k that you see here can actually be computed out. So, basically you have at xk and you have to go to dk, you use dk as your direction along with which you move, and you compute xk plus 1, and then you find out alpha k, right. So, to what extent you will go, so that you maintain a drop in the, or you minimize the function f of xk plus alpha k dk, and you find an alpha k which minimizes this function. Basically what you do, you try to find the alpha over alpha greater than 0, you minimize the function f of xk plus alpha dk, but very well you do not know that this dk is a descent direction, you know only that it is a conjugate direction. But this sequence in n steps x naught, x1, x2, x3, x4 dot 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 xn minus 1, xn minus 1 will be the solution of the problem. So, this is a very good approach by which you can actually program in to solve this particular type of problem, and very useful in the case of large number of variables. So, here is our next result, but this again concerns the same function f x. So, consider f x over x H positive definite. Let x naught be an initial guess point, initial guess solution. Okay. Then consider the sequence consider the iterative sequence. X k plus 1 is equal to x k plus alpha k d k, where alpha k is equal to minus g k d k d k h d k. Of course, g k is nothing but h x k plus b. Then this iterative sequence where alpha k is this converges to the unique solution x star. Here what we have done, we have computed every alpha i's and then computed the x star, which is quite a heavy computation if you really want. Here you are generating just sequences, just getting a new data, taking a new, starting with d0, then going to d, when you come to x1, from x1 to go to x2 use d1, from x2 to x3 use d2 and so on, and you keep on generating these points, and these points in finally n steps xn minus 1 would be the solution. Okay. Let us try to give a proof of this fact. So, there is a unique solution to this problem which we know. So, what we can do, and x naught is my starting solution. So, consider x star minus x naught. So, I do not know this whole thing, but okay, I know this solution x naught. So, this can be expressed as summation I equal to 0 to n minus 1 alpha I d I. By the same way that we have evaluated, we can now compute for every k, alpha k is d k h x star minus x naught divided by d k h d k, in the same process that we have used. Now, if you observe what I have done, you have x1 is x naught plus alpha naught d naught, while x2 is nothing but x1 plus alpha 1 d1, right, which is nothing but x naught plus alpha naught d naught plus alpha 1 d1, that is nothing but x naught plus summation I is equal to 0 to 1 alpha I d I. So, basically the iteration x k can be written as x naught plus summation I is equal to 0 to k minus 1 alpha I d I. So, this would immediately imply x k minus x naught is summation I is equal to 0 to k minus 1 alpha I di. So, this is the way things are calculated. So, you know the iterations are also very similar. So, what we will discuss more about this iteration in a short while after we finish doing what we were discussing. So, again observe that h of x k minus x naught is nothing but summation I is equal to 0 to k minus 1 alpha I h of di just by my properties of matrices. Then dk h x k minus x naught is equal to summation I is equal to 1 to k minus 1, I am possibly skipping some steps. So, again in the same way using the these are conjugate directions, because these are conjugate directions for all k not equal to I, this is 0. So, this would finally give me that dk h x k minus sorry so what it should give me. Here I have all I from 0 to k minus 1. So, k is not here. So, for all I from 0 to k minus 1. So, none of the i's are k. So, this would be all 0. So, this is 0. So, this gives me dk h x k is same as dk h x naught. So, alpha k need not now depend on x naught. So, alpha k which we had computed out in this page, this one, this alpha k can now be written as dk, because dk of h x naught is h x k. So, it can be written as dk h x star minus h x k dk h dk. Now, we already know that h x k is nothing but g x g k minus b, that this is nothing but the g k is what, g k is nothing but the gradient of f at x k. So, I can write here that as g k minus b, but what is h x star? H x star is nothing but minus b, because h x star is the unique minimum. So, ultimately alpha k can be now written as minus dk g k. So, you have to put here h x k as g k minus b, and so it will become minus g k plus b, while h x star is minus b. So, that minus b plus b cancels and minus dk g k would be the thing left on the top, and so this alpha k is now. So, that is exactly the alpha k that we wanted. Now, x n, the nth step is x naught plus I is equal to 0 to n minus 1 alpha I di, but x naught plus this and the very beginning what we have written, this is x star is equal to x naught plus summation alpha I di. And now, from our iteration scheme we have x n equal to x naught plus I equal to 0 to n minus 1 alpha I di, and this is nothing but x star. So, the x n is nothing but x star. So, after iteration from 0 to n minus 1, you have done in n minus 1 step, in n steps you have reached the solution. So, this is a very beautiful thing about conjugate directions method. So, that shows, that gives us a possible hope that we can use this method flexibly for certain classes of problems which need not be so nice, that it need not be a quadratic function with positive definition that is having a unique solution. So, even if they are non-unique solution, there must be some ways to handle such problems using this trick. So, we will tell a little bit more about this iteration to your mind. If I was a student in your place, I would first ask the question, that how do I get all those conjugate directions? How do I know? How do you? I cannot just arbitrarily try finding this is a conjugate direction, take the h and try to do this straight. Okay, I am being given the same function, same problem as before, minimize f(x), like the same one, the quadratic function with positive definite Hessian, but that is not the real question. The question is, how do I know that how to generate my conjugate directions? Now, before I tell you that how do I start generating conjugate directions. So, I cannot generate it from the blue, I cannot just take arbitrary in vectors and then try all those things with h, that is stupidity and waste of time. So, numerical optimization, the important thing is that you must tell me how to generate each of the objects that I need, and then before I tell you how to do that, let me now give you a few homework. Actually, this is not very difficult, so you can try it out. If you are stuck, maybe we can try it out later on. So, consider the hypothesis of consider the problem in the above result, same problem in the above result. Then show that gk di is equal to 0 for all I till k, not k, to k minus 1. So, basically for all I till k, the gradient that you obtain is actually perpendicular to the conjugate directions till k. There you have not reached k, here they are strictly less than 0, strictly less than k, and the choice of alpha k is equal to alpha k with this alpha k, the choice alpha k minimizes f(x) on each line x equal to x k minus 1 plus alpha di for. So, this would be homework which I am not going to explain in detail now. So, our next attempt is how to find the conjugate directions. How to find the conjugate directions. Now, this attempt, this leads to the conjugate gradient methods. So, consider the same problem which I am writing again, but I do not think I would like to repeat it every time. So, there are two results which I want to write down. If h is positive definite, then for any initial x naught, initial choice x naught. So, for any initial choice x naught, consider my initial direction d naught as minus g naught which is nothing but now this then generate the iterative sequence where alpha k as before and of course you have where g k of course is the gradient at x k, which is b plus h x k, and d k plus 1 minus g k plus 1 plus beta k d k with beta k. This is a very important scale factor now, because it allows you to find from. So, if I have d 0, so d 1 is minus g 1 plus beta 0 d 0. So, that is how I am generating the orthogonal, the conjugate directions. We really have to prove that these are conjugate directions, then only we can you apply the previous result. G k plus 1 inner product h d k, this is a very nice. So, this is a very standard denominator in conjugate gradient method. So, this is what you will have, and so then generate the iterative sequence this. Then the iterative sequence converges to the unique solution x star in n steps of course. And B, we have g k g I is equal to 0 for, so it is for g k is orthogonal to all the other g i's whenever I is strictly less than k. So, this is what we are going to prove in the next class, and once we prove this we will write down the conjugate gradient algorithm. Now, there are various ways of choosing this beta k, and that leads to various types of conjugate gradient algorithms, especially when you are talking about non-convex or minimization of non-quadratic functions. You have very different types of that leads to methods like Fletcher-Reeves method, Powell's method, and so on and so forth. So, we will for example, do in detail the Powell's, we will write down the Fletcher-Reeves algorithm, but we will write down also in detail, we will study in detail the Powell's algorithm including the proofs. So, that would be a very good introduction to the conjugate gradient methods, and then we will switch over to quasi Newton methods. So, that is our plan for the few coming lectures, and then once that is over we will try to understand a bit about trust region methods, which are very modern techniques which are being used at present and studied and understood at present, and then go over to the convergent to the theory of nonlinear optimization, largely of in constant optimization, where we will start talking about the Karush-Kuhn-Tucker conditions and related issues. So, thank you very much for the attention.